The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone. We at Hosokawa Micron Powder Systems welcome you and thank you for attending our next in the series of educational webinars entitled Basics of Size Reduction, Part 2. Let me point out, if you have a question during this presentation, you may submit your question online. Please refer to the question and answer pane on your screen. At the conclusion of the webinar, we will try to accommodate all of the questions during our question and answer forum. My name is Bill Brown. I am the manager of the Chemicals and Minerals Group at Hosokawa Micron Powder Systems. Hosokawa Micron Powder Systems is a division of the Hosokawa Micron Group with headquarters in Osaka, Japan. We are the global leader in powder processing equipment manufacturing, employing over 1,500 employees worldwide with production facilities in 5 countries and 12 research facilities and state-of-the-art test centers. Hosokawa Micron Powder Systems is the North American division of the Hosokawa Micron Group, supplying products and services in the chemicals, minerals, food, and pharmaceutical markets. Our brand names include Micro, Alpine, Micron, Briconauta, Majak, Stott, and Vital Air. Our division was founded in 1923 under the name Pulverizing Machinery. We are located in Summit, New Jersey and have approximately 50 employees and have been part of the Hosokawa Micron Group for 23 years. At this point, I would like to turn the presentation over to Mr. Rob Voorhees, Vice President and General Manager of the Hosokawa Micron Powder Systems. Rob has worked in the processing industry for the past 30 years. Rob started his career with the Micropool Corporation, an air pollution control and environmental company that was acquired by Hosokawa in 1985. He later worked for several years as regional sales manager for Research Control Corporation. In 1994, he rejoined the Hosokawa Micron Group. Rob held various sales and management positions until becoming general manager in 1998.
Good afternoon. My name is Rob Voorhees, and I will be the presenter for today's webinar. Welcome to Part 2 of our presentation on basic size reduction. The overview of basic size reduction today will cover the subjects of fine and ultrafine grinding, general mill types, operating principles, application information, and basic system concepts and system components. In Part 1, we discussed the 4 basic principles utilized in milling equipment for the purpose of dry particle size reduction. They were shearing or cutting, attrition, compression, and impact. In many cases, a combination of these principles may be employed in any one machine. The fine grinding machines we will discuss today employ primarily the principle of impact grinding. The subjects covered today will be fine to ultrafine particle size reduction. For the purpose of defining these categories, fine size reduction will be defined as particles ranging from approximately 50 microns in diameter down to 20 microns in diameter. Ultrafine size reduction will be defined as particles that range from 20 microns down to 1 micron or less. Coarse grinding and medium grinding, noted in red, were the topic of our webinar last month. For those of you who were unable to participate, you can view this webinar and review grinding principles and particle size definition by visiting our website and viewing our educational center. Today we'll look at size reduction using the grinding principle of impact. Impact is defined as a solid object moving at high velocity coming in contact with a stationary particle. The impact principle is employed in all 3 of the machine types we will discuss today: air classifier mills, spiral jet mills, and fluidized bed jet mills. Impact is used to achieve the highest fineness possible in these types of machines. Most hard crystalline and amorphous particles react very well to impact for the purpose of size reduction. The most important aspect of selecting a size reduction method is to know some basic information about the product you want to produce and the raw material it is made from. The 4 basic things you should know are particle size of the feed material, the material's characteristics, the required end product particle size, and the required end product particle size distribution. Knowing this information will help you and the equipment manufacturer to make the proper equipment selection. It is important to note that based on product characteristics, only certain milling technologies can be employed for a given application. Starting a project understanding these basic requirements will result in an economical and trouble-free milling system solution for your powder processing application. It is also recommended to do test trials on a pilot scale piece of equipment. Almost all equipment manufacturers offer customers the capability to do in-house test trials. Important information on system design and scale-up are learned during these trials. In part 1 of basic size reduction, we talked about material characteristics and how they affect milling system performance. Let's review it again now. Let's look at the effect of feed size on mill performance. Larger feed material means more residence time in the mill, and larger equipment will be required for a given production capacity. Feed size affects feeding methods and feeder selection. For example, air conveying large size, high bulk density feed to a mill may not be possible, and large feed material cannot be introduced to spiral jet mills using injector feed. How does bulk density affect performance? Bulk density affects flowability of the product. Feeding can also be affected. Light density materials may flood past the feeder, affecting feeding accuracy. There are methods available to determine the flood and flow characteristics of materials. Bulk density will also affect the sizing of hoppers and finished packaging. Light bulk density material will affect grinding efficiency, as lighter materials are more difficult to keep in the grinding zone. Cohesive products can cause numerous problems in a milling system as well. Cohesive and sticky products may build up on mill internals and can upset airflow and increase pressure drop across the mill. Systems may require the use of high-velocity air to keep mill internals clean. Heat-sensitive products also require special handling and special system designs. Low melt point materials are sensitive to mill systems with high energy input. Heat-sensitive products may require cooling in order to efficiently process them. What about product moisture and products with moisture-absorbing characteristics? Hydroscopic materials absorb moisture, causing buildup and plugging, and may require dehumidified air for processing. On the other hand, products containing moisture may allow for high-energy processing. The moisture in the product will absorb the heat of grinding, providing cooling in the process. Material hardness also needs to be considered when selecting a milling technology. High-energy milling may be required to effectively break very hard particles. Material hardness may lead to high component wear and increased maintenance, minimizing the selection of equipment for abrasive applications. Special wear protection of mill components may need to be considered. Fluidized bed jet mills are particularly suitable for this type of application. On the other hand, there are friable materials and materials that fracture easily. High energy input can lead to too many fines generation when handling friable materials. Low energy processing may have to be employed when handling these types of products. If particle size and shape is important, keep in mind that impact tends to produce sharp angular particles. Compression and shear forces tend to produce more rounded particles, and high aspect ratio materials are destroyed by impact forces. You can see that material characteristics play a very large role in machine selection and design. Let's move on to talk about milling technologies. This chart is designed as a very basic selection method for milling equipment when considering end particle size requirements and the hardness of the material to be processed. As you can see, only certain mill types are suited for very hard materials. This is mainly because hardness is also associated with mill wear, and certain milling technologies lend themselves much better to process hard and abrasive materials. Some of the mills we will discuss today can process very hard materials. All the mills we will discuss today can be wear protected, and certain types of jet mills can grind extremely hard materials that cannot be processed in other types of impact mills. Today we'll focus on fine and ultrafine size reduction categories shown here in yellow and purple. We will cover generic types of machines including air classifier mills, spiral jet mills, and fluidized bed jet mills. Please note that there are many sizes and configurations of machines available in the marketplace. We will discuss only a few generic machine types today, but the discussion should provide you with a general overview of the basic technologies available. The first mill type we will cover is the generic air classifier mill. Air classifying mills are probably the most widely used milling technology in the powder processing industry today for general size reduction of fine chemicals and food products. These types of mills are very versatile and allow operators to produce fine products with narrow size distributions. Unlike mills discussed in Part 1 that basically use screens of various sizes to control particle size, in the air classifier mill, particle size is easily controlled by adjusting the speed of an internal classifier wheel. These mills incorporate impact grinding and air classification in a single process. The main principle of this mill type is to use air to convey material to the mill, classify the product into fine and coarse fractions, convey the fines out of the mill, and then return the coarse fraction to the grinding chamber for further size reduction. This process is repeated on a continuous basis. The unique feature of this type of mill is that the classification step takes place inside the mill and is not a separate or external operation. This design allows these mills to be relatively compact and small in size. The main airflow is introduced from underneath the main rotor disc as shown here. Material is introduced into the grinding chamber at the grinding zone and is impacted by the rotating hammers shown here. Processed material is then carried by the airstream to the classification zone shown here. Correctly sized material passes the classifier and exits the mill here. Oversized material is rejected by the classifier and is returned to the grinding zone. The grinding and classification zones are normally separated by a shroud and baffle assembly shown here. The impact rotor and classifier have separate or independent drives so that the speeds of each component can be adjusted independently. Some mill designs incorporate coaxial design drives as shown here. This design is a drive shaft within a drive shaft and provides a mill design that is very compact with a low overall machine height. Independently driven mills are much taller but also offer advantages when close coupling of the mill with a cyclone or product collector is desired. Air classifier mills can be used for a wide variety of applications. Due to the requirement of a large volume of air, heat-sensitive materials can easily be processed. The makeup air to the mill can also be conditioned so that humidity and temperature can be controlled when processing hydroscopic or heat-sensitive materials. Heat can also be added to provide drying when lower levels of moisture need to be removed from the product. A wide variety of designs and sizes are available. Small units as low as 1 horsepower are capable of handling a few kilograms of material and are available for pilot scale and research and development use. Sanitary designs are available for handling pharmaceutical and food grade products and when special cleaning and sanitary requirements need to be addressed. Large capacity mills of 500 horsepower and more are designed with special wear protected internal components. These mills are available for minerals-related applications or for materials that are somewhat abrasive in nature. For handling materials that present an explosion potential, these mills can be designed to handle an overpressure of 150 psi. To minimize the potential for unexpected drive failures, the bearing housings of these mills can be supplied with both vibration and bearing temperature sensors. These devices will allow the operator to know when problems become present before a failure actually takes place. Let's look at some other designs that function the same but are designed differently. Another type of air classifier mill is one with a horizontal classifier wheel. While in principle it functions the same as the vertical wheel mill, due to the wheel orientation, the shroud and baffle assembly is not possibly used to separate the grinding zone from the classification zone. So to provide a separation between these two zones, the housing is extended to allow room for the product to circulate within the mill. This mill type is usually much taller in height and cannot be provided with a coaxial drive assembly. Another type of air classifying mill is one that has both the main rotor and the classifier mounted on one shaft rotating at the same speed. While this type of mill offers a reduction in size, cost, and installed horsepower, There is also a loss of flexibility in adjusting the final product specification. This type of mill may be a good option when only one specific product is reproduced and no changes in end product fineness are required. Another example is the type of air classifier mill shown here. The orientation of the grinding chamber is now on a different axis. In this mill, the oversized material is rejected by the classifier and is ejected from the mill. This type of throwout device can be provided in almost all classifier mill types. The advantage is that hard, ungrindable materials can be taken out of the mill chamber, reducing component wear and horsepower consumption. Brightness and color quality can also be improved with the removal of impurities. This picture shows yet again another mill design which is available for customers that need to clean the mill on a frequent basis. You will notice that this mill has an additional external chamber. The mill liner now stands alone as shown here. All the internal components are easily accessible and removable for cleaning. The external chamber now acts as a vessel that allows the operator to clean the mill and contain the effluent inside the chamber. Usually a ball valve is provided at the bottom of the chamber as a drain. Let's talk about the operation of the air classifier mill and the important operating parameters. While the classifier speed has a large effect on particle size, airflow can also be adjusted to change particle size. While the primary purpose of the classifier is to control particle top size, the mill internal components can also be changed to adjust particle size distribution. As an example, the standard liner configuration supplied with these mills types is a multiple deflector liner. This liner type has vertical grooves designed into the circumference of the liner. If you recall from our discussion on our last webinar on hammer mills, this type of liner serves the purpose of slowing the circumferential speed of the particles and deflecting them back into the path of the rotating hammer, maximizing the impact force of the particle. The liner type can also be changed to reduce the generation of fines or to make an overall coarser size distribution. The use of smooth liners in the grinding chamber will decrease the impact force of the hammer that is applied to the particle. The impact hammer design will also affect the impact force and thus affect end product size. An alternate type of impact hammer shown here is the pin. Use of a pin rotor reduces the impact force, providing a coarser grind, and minimizes the generation of fines. Rotor speed can also be reduced to minimize generation of fines. When we talk about air classifier mills, we should also discuss the theory behind classification technology used in these mills. This diagram shows a top view of a radial-bladed classifier wheel. The various forces that come into play during operation are listed on the diagram, and the formula for the calculation of the cut point is shown. The yellow dot represents a particle. You can see that there are two forces at work on this particle as it approaches the classifier wheel. There is a drag force or centripetal force generated by the airflow traveling toward the wheel. There is also a mass force or centrifugal force generated by the rotating classifier wheel on the particle. When these two forces are balanced for a specific particle mass, the particle will have a 50-50 chance of either being accepted or rejected by the classifier. So by varying these forces, a specific particle size or cut point can be attained. You can see from the formula that with all values held constant, the cut point will vary with the square of the tip speed of the classifier wheel. The result of this relationship is that a small change in classifier wheel speed has a large effect on the change in particle size. Several classifier wheel types are available depending upon the application. The number of blades and the height of the wheel can vary to allow for different surface areas, changing the velocity of the airflow through the wheel and hence the performance of the mill. This chart shows the basic relationship between the system air volume and the classifier wheel speed. From a practical system operational standpoint, it is desirable to maintain a constant airflow during operation. So to adjust particle size, the speed of the classifier wheel can be adjusted up or down to produce a finer or coarser particle. Air classifier mills offer many benefits, including exact particle size control, flexibility to easily change particle size, compact system design, economical operation, consistent product quality, and a large production capacity. Examples of the variety of applications these mills can handle are shown here. Adjustment of airflow and classifier speed allow the attainment of many different product sizes as shown. Examples of rates are also shown for specific materials. These rates can be used to determine the production mill size based upon the total system capacity desired. As an example, if you wanted to process talc to 45 microns at 4.5 tons per hour, you would divide 9,000 pounds per hour by 45 pounds per horsepower per hour to arrive at the required production machine horsepower of 200 horsepower. This is a system diagram of a typical air classifier mill system. The basic components consist of a feeder to meter the material to the mill, in some but not all cases an isolation device such as a rotary airlock, the air classifier mill itself, a product collector, and a fan to generate the system airflow requirements. In some cases, safety filters, as shown here, are also included in the system. These filters prevent material leakage from the product collector from affecting fan and heat exchanger performance. It is almost always desirable to maintain a constant airflow to ensure product quality and reproducibility. The classifier is the primary device used to adjust particle size. In all cases, the main drive amperage of the mill is used to control the feed rate to the mill. For maximum production, these mill systems are very often run at 95 to 100% of the full load amperage of the main drive motor of the mill. When operating with conditioned air or nitrogen, energy savings becomes a major consideration. In these cases, closed-loop systems can be supplied to maximize energy savings, as the recycled gas can be reused, reducing nitrogen consumption, or for the reclaiming of heated or cooled gas. The closed-loop system incorporates the additional elements of a heat exchanger and additional controls and valving to bleed off excess gas and control system pressure. This last picture shows an actual air classifier mill installation. This is a 40 horsepower mill with a floor-side pneumatic feeding setup. The system is designed for overpressure containment in the event of an explosion and has explosion barrier valves incorporated into the design, as shown here in red, to contain the overpressure within the system, protecting the local environment and the personnel in it. The product collector is shown mounted on a mezzanine with the finished product discharge at the ground floor level. Let's move on to ultrafine grinding. The presentation today will cover spiral jet mills, sometimes also referred to as pancake jet mills, and lastly, fluidized bed jet mills. These mill types are often used for producing very fine grinds. Remember earlier we defined ultrafine grinding as end product fineness ranging from 20 microns down to 1 micron and below. There are also other types of jet mills, such as loop type mills and target type jet mills, but we will not discuss them today. Shown here is a clear picture of the internals of a spiral jet mill. You can clearly see the feed injector at the top of the grinding chamber. At the outside of the grinding chamber is the air ring manifold, which allows the compressed gas to be distributed to the nozzles. The nozzle ring incorporates several nozzles around its perimeter to evenly distribute grind air to the mill chamber. The outlet is shown at the center of the mill. This is a cross-sectional view of a spiral jet mill. The basic design is simple and incorporates no moving parts. Compressed gas is used to effect both size reduction and to introduce feed into the mill. A series of nozzles located around the perimeter of the grinding chamber allows the introduction of grinding air. The orifice at the center of the grinding chamber provides an outlet for the finished product. These mills do not have an internal classifier in their design. In a spiral jet mill, particles are reduced in size by interparticle collisions and impact against the grinding chamber wall. Coarse particles are subject to centrifugal forces and stay in the grinding chamber longer for further size reduction. Fine particles are subject to the drag force of the airflow and are drawn to the center of the grinding chamber and exit the mill through the outlet orifice. Spiral jet mills are very often utilized in the pharmaceutical industry for their capability to produce very fine, particle size distributions. Their simple design makes them much more suitable for cleaning and validation requirements. Shown here is a 12-inch diameter spiral jet mill designed with the materials of construction and finishes required of the pharmaceutical industry. This mill skid incorporates the feeder and controls on one portable skid. The product collector in this case is a separate unit. Jet mills like this one are available for small-scale processing. They are designed to handle very small volumes of material down to less than 5 micrograms and can achieve very high yields due to small internal surface area of the mill and local product collection. These small mills are easily incorporated into glove boxes and isolators when the need arises to handle toxic compounds. The complete system, including feeder, can be driven by compressed gas, eliminating any problems meeting Class 1 electrical requirements. Another relatively new development is the disposable jet mill. The main body and material contact components of this mill are made from PVDF, a corrosion-resistant polymer. Small quantities of potent compounds that require a minimal amount of exposure or that are difficult to clean can be processed in this type of mill. Upon completion of the milling campaign, the low-cost main components of the mill can be disposed of, eliminating the need for cleaning and validation. Now let's discuss the operational parameters of this type of jet mill. The cut point on a spiral jet mill is a function of the total air volume and the ratio of grinding air to injector air. The following fundamental relationships will help you understand the effects of these parameters on the performance of the mill. A high grinding air pressure produces a finer end product, but also a higher amount of oversize in the fines. A low injector air pressure produces a lower suction at the feed intake and negatively affects the feed intake to the mill. A high injector pressure will result in a coarser grind due to the shorter residence time of the material in the mill because of the higher overall total air volume. Feed rate will also affect particle size. A higher feed rate will result in a coarser product. In order to achieve the desired end product at the maximum throughput, both airflows must be optimized. To prevent product blowback at the feed, the injector air pressure must always be equal to or higher than the grinding air pressure. To maintain a consistent end product, the feed rate and grinding air pressure must be kept constant. Altering the end product fineness can also be accomplished by changing other parameters. The angle of incidence is defined as the nozzle angle as measured from the radius of the grinding chamber. A steep angle of incidence of 30 degrees will result in a shorter material residence time in the mill and a resultant coarser end product. A wider angle of incidence of 50 degrees will result in a longer material residence time in the mill and a resultant finer end product. Nozzle diameters also affect end product fineness. All other operating parameters being held constant, larger diameter nozzles will result in lower grinding air velocity and result in coarser end product. Smaller diameter nozzles will result in a higher grinding air velocity and a finer end product. The number of nozzles can be changed with different effect. All other operating parameters being held constant, a greater number of nozzles will result in a lower grinding air velocity and result in coarser product. A lesser number of nozzles results in a higher grinding air velocity and a resultant finer end product. This chart graphically depicts the results that the changes of process and component parameters have on end product fineness. This chart will help you better understand the basic operating variables of a spiral jet mill and how they affect end product fineness. As an example of spiral jet mill performance, the information shown here was developed using a 12-inch diameter spiral jet mill. The product finenesses and throughputs are nominal values and can change depending upon the actual product to be milled. Here are some of the benefits and limitations of these mill types that you should consider when deciding whether to choose this technology for your application. They are both simple in design and simple to operate. No moving parts means reliable operation, and they are very easy to disassemble, inspect, and clean. Their limitations include the lack of good internal particle classification, which very often leads to oversized particles, and the requirement to overgrind or regrind to achieve the final desired particle size distribution. Buildup can occur when processing sticky materials, affecting the final particle size distribution and processing time. Heat-sensitive and abrasive materials are sometimes difficult to process in spiral jet mills. This chart gives you a summary of the basic capabilities of these jet mills. Most of these topics we have already covered in the presentation, but I'll review them again here. Particle size distribution is wide because of the lack of classification. Energy consumption is higher due to the requirement for overgrinding. This type of jet mill is not well suited for processing sticky and heat-sensitive materials. The noise level is high due to the high velocity compressed gas. Feed size is limited by the nozzle size of the injector feed. This type of jet mill is not well suited to process abrasive materials. Cleanability is very good, as there are few components and disassembly is easy. And lastly, high pressure designs are available for specific applications. Let's move on to talk about fluidized bed jet mills. The fluidized bed jet mill design and functionality is quite different from the spiral jet mill. Size reduction actually takes place within the bed of material, where particle-to-particle collision results in the reduction of particle size. Fluidized bed jet mill designs incorporate a grinding zone as shown here at the bottom of the mill chamber. The classification zone is located at the top section of the mill. Feed material can be introduced to the mill either through a top gravity feed inlet as shown here or directly into the fluidized bed at the bottom of the mill. These mills work by accelerating a gas through a nozzle directed to a central focal point. Multiple nozzles are used to generate a grinding zone at the center of the mill. The material bed height in these mills will completely cover the nozzles during operation. Only gas and not product is fired through the nozzles. The high velocity gas entrains the material in the bed, and the combined gas-material mixture is directed to the central grinding zone. Particle-to-particle collision is responsible for size reduction. Fine material is carried by the upward flow of air to the classifier wheel, where material ground fine enough exits the mill, and oversized material is returned to the grinding chamber. Please refer back to our discussion on the theory of classification for air classifier mills. The concept and formula for cut point determination with a dynamic classifier wheel are the same. Most applications utilize top gravity feed. However, applications where very light density materials are reprocessed can utilize a bottom feed. This ensures that product gets into the fluidized bed and does not float at the area around the classifier, reducing both mill capacity and efficiency. Most designs allow for easy removal of the nozzles so that they can be changed from the outside of the mill. This makes maintenance and product specification changes much easier. All designs incorporate a radial nozzle arrangement with the number of nozzles used varying with the mill size. In general, the larger the mill, the higher the quantity of nozzles utilized in order to introduce the correct volume of air required for grinding. Different types of nozzles are also available depending upon the application. An additional vertically oriented nozzle can be added to the bottom of the grinding chamber to assist in the fluidization of high bulk density materials. The grinding of metal powders usually requires this type of mill design. The feed rate to the mill can either be controlled by the amperage of the classifier, or a preferred method is to provide the mill on load cells so that the bed weight and height can be better maintained for stable mill performance and uniform product feed. Mill designs, materials of construction, and finishes are available for all applications. Designs are available for handling materials that are potential explosion hazards. Due to the high volumes of gas utilized in processing, in most cases it is not economical to process materials using inert gas. For those materials that are potential explosion hazards, the mills can be designed for high overpressure, effectively containing any explosion that may occur. For the processing of extremely abrasive materials, these mills can be lined with ceramics or polyurethane. New technology allows for the high wear components, particularly the classifier, to be made in silicon carbide or cast aluminum oxide, providing thousands of hours of service life when processing abrasive materials. The function of nozzle size and grinding pressure has the same end result as we already saw with the spiral jet mill. The difference with this type of jet mill is the addition of the internal classifier. This chart graphically depicts the results that the changes of process and component parameters have on the end product fineness. This chart will help you to better understand the basic operating variables of a fluidized bed jet mill and how they affect end product fineness. Here are some of the benefits and limitations of these mill types that you should consider when deciding whether to choose this technology for your application. These mills produce the finest particle size with the steepest particle size distribution. Materials that require minimum ferrous contamination, that are heat sensitive, or that are highly abrasive can be easily processed in the fluidized bed jet mill. Operating costs are minimized as energy consumption is reduced as correctly sized particles exit the mill immediately. Unlike spiral jet mills, using a large feed size is possible due to the large feed inlet. As an example of fluidized bed jet mill performance, the information shown was developed using a 16-inch diameter mill. The product finenesses and throughputs are nominal values and can change depending upon the actual product to be milled. This graph shows the performance relationship between a spiral jet mill and a fluidized bed jet mill processing the same material. The fluidized bed jet mill can provide a finer top size due to its internal classification capabilities. The spiral jet mill shows a higher amount of fines due to the overgrinding required to achieve a similar top size as the fluidized bed jet mill. The fluidized bed jet mill, as shown here, is capable of producing a much steeper particle size distribution with lower overall energy consumption. Fluidized bed jet mills can handle a much wider application range than spiral jet mills. Due to their operating principle, they can handle extremely abrasive materials as particles are impacted against each other and not against the internal components of the mill. Very heat-sensitive materials can be processed due to the rapid cooling of the grinding air as it expands in the grinding chamber. Soft and sticky material can be processed as buildup is eliminated due to the particle-to-particle impact, not particle-to-grinding chamber impact. Materials requiring a high degree of brightness or purity can be processed in these mills as most contact with ferrous components are eliminated or ceramic components can be used to minimize ferrous contamination almost altogether. This chart gives you a summary of the basic capabilities of these jet mills. Most of the topics we have already covered in the presentation, but I'll review them again with you here. Particle size distribution is steep due to the capability of the internal classification. Energy consumption is lower due to a more efficient grinding and classification process. This type of jet mill is well suited for handling heat-sensitive and sticky products. Noise generation is low as the material bed dampens the noise emanating from the high-velocity grinding gas. A wide range of feed size is possible. This type of jet mill also is particularly well suited for handling abrasive materials. And cleanability is good as clean-in-place system designs are available. Lastly, high-pressure mill designs are available for handling materials that present potential explosion hazards. This is a process flow diagram depicting a fluidized bed jet mill installation and the system components that are required. In the design of the fluidized bed jet mill system, the mill typically will operate at either zero or a slightly negative pressure in the grinding chamber. The system fan is sized to maintain this pressure, and a pressure transmitter located in the grinding chamber senses the chamber pressure and provides feedback to the system fan in order to maintain a constant mill pressure and airflow. This is a picture of an actual fluidized bed jet mill installation. Here you can see the mill suspended from tension load cells. The grinding air manifold is located at the base of the mill. Located behind the mill and against the back wall is the system air manifold assembly. This manifold contains pressure regulators for the grind air, bearing purge air, classifier gap purge, and other system requirements such as air required for operating valves and for the product collector reverse pulse jet air. Several types of ball mills and medium mills can produce ultrafine grinds as well. In many cases, they are a more cost-effective solution for ultrafine grinding of large quantities of materials at high throughput rates. Their kilowatt per ton of material power consumption cost is usually much lower than that of a jet mill. If you would like to know more about these technologies, you can visit our website and educational center where you will find a presentation on wet and dry media milling. This concludes our presentation today on fine and ultrafine basic size reduction. I hope you found the information today informative, and I thank you for your participation. Please look for our future webinars. Thank you.
Now we begin our question and answer forum. As we're limited on time, we will try to accommodate all the questions, but apologize in advance if we are not able to answer all of them. If we are not able to answer or address your question at this time, someone from Hosokawa will respond to you offline at a later date. The first question I see here: does feed rate into an air classifying mill affect the product particle size?
Usually not. The only time that feed rate should affect the particle size in an air classifying mill is that if you overload or exceed the maximum feed rate and overload the classifier wheel, in which case you would see a high amperage load on the classifier. In that case, you could get some oversized particles through the air classifying mill.
How does the energy consumption of a fluidized bed jet mill compare with that of a pancake or spiral jet mill?
The energy consumption of a fluidized bed jet mill is typically lower than that of a spiral jet mill. It will depend on the application, but as a general rule of thumb, the power consumption could be as low as, say, 70% of a spiral jet mill.
What pressure is utilized at the jets of a fluidized bed jet mill?
The grinding pressure of a jet mill can vary. Typically, it's in the range of 80 to 90 psi, but it can vary from as low as 30 psi to even 125 psi, depending upon the application and the amount of energy that you would require to produce the particle size that you want.
How does the energy consumption of a ball mill compare with that of a fluidized bed jet mill?
Typically, ball mill systems are used for much higher throughput. I think, as I mentioned in the presentation, the typical kilowatt per ton power consumption of a ball mill is far less than that of a fluidized bed jet mill.
Are any of the spiral jet mills, fluidized bed jet mills, or air classifier mills available in a cryogenic mode?
In theory, they all can operate cryogenically. It really depends on the application. You don't see it used that often, but it can be done.
What is the difference in gas consumption for an air classifying mill between an open loop system compared to that of a closed loop system?
I assume the question you're asking is about the use of nitrogen for inerting. The operation of these mills, typically what will happen is during startup you'll flood the mill with nitrogen to reduce the oxygen level. And then with the closed loop system design, you will trickle in nitrogen to maintain a certain oxygen level content. But once the mill is flooded, you can typically operate at, say, 20% of the total nitrogen consumption that you would use during the initial flooding of the mill.
Can all the milling technologies mentioned operate in an explosive environment?
The answer to that is yes. All the technologies discussed today can be designed for either containment or inerting to protect the plant environment and operators when handling potential explosive hazardous materials.
How does a particle size distribution differ between the fluidized bed jet mill and the spiral jet mill?
If you refer back to our presentation, I think we showed a slide on that. Due to the internal classification, the fluidized bed jet mill particle size distribution is usually much steeper. Because the particles exit the mill chamber as soon as they're ground, the fines generation is much less and the top size is controlled much better, and the end result is a very steep particle size distribution.
That concludes our question and answer forum. Again, if we were not able to address your question, we will offline at some point after this particular presentation. We at Hosokawa Micron Powder Systems sincerely thank you for your time and attention today. Please refer to our website, hmicronpowder.com, to view upcoming educational webinars. If you have any questions or requests, you may contact Rob Voorhees. His contact information is displayed here. One other note, this presentation will be posted on our website, so if you know of any colleagues who may be interested in viewing this at a later time, or prior webinars, they may do so by accessing our website. Again, we thank you, and good day.